Alright, welcome. Today is Monday, March 30th. We're in our third week of online classes. Christian Tran is already saying he doesn't like online classes, wants to go back. Yeah, I want to go back too. However, as you know, we are closed until May 1st. And I believe the president will announce on Tuesday that everything, like the stores and all that stuff, everything should be closed down until at least April 30th, the end of the month. So we're going to go one more month with social distancing and then see if that will help. And then hopefully by May and June we'll start recovering and going back to normal. Right? Today our goal is to finish up Flippy number 6. So this will be our 6th entry. We'll talk a little bit more about circuits and just some basic information, so it should not be too long today. Now this week is the third week. However, there is no school on Friday and spring break is next week. So we only have classes for 4 days, so Monday through Thursday, and then on Friday we'll be off. Starting Friday, because it's Cesar Chavez Day, or at least we're observing Cesar Chavez Day on Friday. And then a week off, and then we'll come back. We'll come back to our online classes on the 13th, right? Is there spring break homework? No, there's no spring break homework. However, you should be planning your theme for your circuit box project. Boo, online classes. Okay. Alright, we have some of you online. That's good. Chapito isn't here today. Usually Chapito is the first one to be here. I guess he didn't wake up on time today. Well, we gotta move on. We gotta carry on for him. Alright, so have your flippies out, or at least take notes so that you can write them in your flippy. Let's go in. Oops. Let's go in title. My chair is squeaky. The title is current and resistance, or should we say electric? No, that's not. So title is current and resistance. And this is what we talked about last week. League of Legends stream again today. No, I don't think so. I still have to do some video processing. I don't know. We did it while the videos were processing, so there was some downtime. But the games kind of take too long, so I don't know. I don't think I can do it. I can't find my flippy. Oh no. Current and resistance is the title. Here's the top side. Top side. The top side will have a bunch of symbols. These are all the circuit symbols. And so when you draw circuits, you'll be using these symbols. Alright. Starting with the battery. If you don't have your flippy, that's fine. Just write it on your OneNote and then you can copy it down later. Or your regular paper is fine. Battery. Here's the symbol for battery. Now we'll use a big line and a small line, like this. Big line, small line. Let me try again. Big line, small line. Okay. The two vertical lines are just wires, so the actual symbol is the big line and the small line, and the two other wires to show you how you would connect them. Alright. Mr. Z, do you like Star Wars? Sort of, yeah. I just don't. I did not like the new set, the 7, 8, 9. Yeah. But I did like the side stories. The side stories are way better than the actual main story. Oh right, Janace's following. Thanks, Janace. Yeah, I thought like what was the side story? Like Rogue One, that was really cool. Even the Han Solo movie was decent. Of course, he was a Jedi for last Hall. Oh yeah, yeah. Christian Chan remembers. Me neither. Not very good. Okay. So battery is a big line and a small line, uh, and then you could also kind of double up, and we'll talk about this at a later time. This is it's similar. You could imagine it as like a bigger battery. It's just big line, small line, big line, small line. Of course, there is a term, and if you'd like to learn more terms, consider taking AP Physics next year. But we will just call this, a big battery. Technically, this is like an ideal battery in that it has, it's perfect. It gives you the same voltage all the time, called an electromotive force, EMF. All this stuff is not necessary for honors physics. We can use either. Just think of it as a single small battery, big battery. Question mark? What's your question, Kuya Casey? Oops. Oh, okay. Is your dog running all over your keyboard like Maddie's dog or whatever? Resistor is the next one. Resistor. The resistor, remember, is what slows down the flow of current in your system. We can draw it with like a squiggly, so zigzag, 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 like that. Okay. Now you can draw these vertically like I have here, or you can have it horizontal, or you can have it sideways. So it doesn't really matter. You are able to rotate them however way you want, and put them in your. I don't think I can rotate. No, I can't rotate. You can put them in your system, whichever direction. It's just the actual design, the symbol. If it's like zigzag, then you'll know that it is a resistor. Whether it's horizontally aligned or vertically aligned doesn't matter. Okay, so that's the symbol for a resistor. The next one is a wire. Let me put some colons. Wire is just a straight line. So you can either have horizontal wire or vertical wire. Doesn't really matter. It's just a straight line. And so any straight line or line segment that you see inside a circuit diagram, that is just a wire. And all wires are ideal for us. So when we're doing problems, we're going to imagine that they are ideal. Which means that it has no resistance. So if you see wires in a circuit diagram, they have zero resistance. However, realistic wires can have resistance, and we got that equation last time. It's R is equal to rho times L over A. The longer it is, the more resistance. The smaller. Oh, we have another follower. Very cool. The smaller it is, the more resistance. Hey, it's Liam. Hey, our period 1 gang is strong. The other classes are not as. I guess it's kind of hard to wake up in the morning, so I shouldn't say anything. But thank you for waking up in the morning and joining us. Alright, so wires, when you see them in per period 1 represent. Yeah. Hey, there's Chapito. Welcome, Chapito. We were saying how today was the first time you weren't the first person to be on. Alright. So the wire is ideal and it has zero resistance. Give me some props. We'll give you a wireless high five, Giorgio, for being period 6 and waking up at 8. Alright. Next up is a light bulb. A light bulb. And if you recall our circuit kit, we used a light bulb to light it up. It was lit. Light bulb. Here we are. Hey, there's Dennis too. Oh yeah, Dennis is in period 6. Cool, cool. There we go. Now people are chatting. Light bulb. The light bulb is almost like a resistor in that it gets so hot that it starts to glow. It gets so hot that it starts to glow. The simplified version is to use like a resistor, a zigzag, with a circle around it. Okay, so if it's circled, then it's a light bulb. There is another version where you can do curly, big curly, small curly, and then wire, and then put a circle around that. So you can do zigzag or triple curly. Either way works. Yeah. I didn't hear him say it. Say what? Did anyone else hear say? No, you heard nothing, Victoria. You heard nothing. Of course, you can always check the VOD. Nah, let's not. It has to be in the moment, you know. Of course, you know the past tense of lighting up a light bulb is what, guys? If a light bulb has already been turned on, what do you say? There you go. Alright. Switch is the next one. So we know, you know, this is how we turn on our circuits. A switch is like a drawbridge. So we have a little ramp-like thing, and then the other part of the wire. So this is the switch. Oh, whoops! I should have wrote the word switch first. Here, there we go. Switch. I can't see the C. There we have it. Switch, not the Nintendo Switch. An electrical switch. I'll make breakfast and listen to Mr. Z's morning podcast. Alright, so this drawbridge, you can, you know, put it down. When you turn it on, what you're doing is you're dropping the bridge, connecting it, and the switch becomes like a wire, and it allows the current to flow through. Wow, we're getting so many followers today. Hey, there's Ria. Ah, it's the entire Genasi gang joining us today. Alright, so that's those are our circuit symbols. These are the circuit symbols. I should write circuit symbols here. The Genasi gang. And then on the side here, we will draw our very first. We're missing Al. Yeah, I know, right? I don't know where Alan showed up like the first day, and then he just didn't wake up in the morning ever again. Rudy. Rudy? Was Rudy here? I don't remember. All right. Ohm's law. We'll start here. Ohm's law. Okay. Ohm's law is what kind of shows us how all of these things are related. He was on FT at like 4 a.m. What is FT? Oh, FaceTime. Oh, I see. What, you guys are FaceTiming at 4 a.m.? Ay, ay, ay. So I'm guessing you stayed up until 8 and you're gonna go to bed at like 9 o'clock? Is this your new schedule? uh, I guess this is what college life is like, really. If you have morning classes, you just stay up and then you go to bed at like 10, 11. But once you finish like your freshman and sophomore years, then you can start taking late classes. Mr. Z, say hi to Alan. Hey, Alan. Well, Alan's not here, so I guess you'll have to hear it on the VOD. Hello, Alan. Make sure you wake up early like everyone else, so you can join the party. Oh, by the way, we did hit 100 subscribers on our YouTube channel. Congrats to everyone. This will now we can actually have a custom URL, so it's, I guess it'll be like youtube.com/c/my name or something like that. So we did it. Yay! 100 subscribers. Ohm's law is delta V. Delta V is a change in potential, which is equal to the voltage. The voltage is equal to I times R. So delta V is equal to IR. Now, sometimes, we kind of get lazy and just we start writing V instead of delta V. It's just when you're doing circuits, you'll just have to kind of assume that V is your delta V, so that you don't have to write delta V every time. So sometimes we just write V equals IR instead of delta V every time, because it's just easier. So from here on out, if you see V equals IR, just know that the V is not potential, it's the difference in potential, and the difference in potential is what we call voltage. Right? And then a simple circuit, has a few of these elements. We'll start with a battery. So here's our battery, big line, small line. Now, the symbols do have some sort of alternate or ulterior meaning, or an extra meaning, I should say. The big line is the positive terminal plus of the battery, and the small line is the negative terminal. Okay, continue. All right. What is the I and R in Ohm's law? Ah, yes. So this is from the notes on Friday. If you remember, V is the voltage measured in volts, I is the current measured in amps, and R is resistance measured in ohms. Maybe we'll write this down once again here on the side. Well, the V is voltage measured in capital V, volts. I is current measured in amps, A, or amperes, and R is resistance measured in omega, ohms. Like that. Let's try again. Resistance. The resistance. If you're a Muse fan, you know all about the resistance. Simple circuit, so we have our battery. So again, remember the big line is the positive end and the small line is the negative end. Alright, and to the battery, we'll use our wires, which have zero resistance, and connect it to a resistor. And resistor is the zigzaggy thing. So zigzag, zigzag, zigzag. And technically, it doesn't really matter how many zigzags you do. I usually try to do 3 at least. And again, it doesn't matter as long as we can tell they're zigzags. There's no real we'll call this resistor R. We'll call this our delta V, our voltage delta V. And current is the flow itself. And remember, current is the flow of positive charges from high potential to low potential. The positive side of the battery, the big line, is the high potential, and the bottom side is the low potential, the minus. So these charges will want to move from high to low, but notice how there's a gap in the symbol. That gap represents a barrier that the charges can't flow through. So instead of going from plus to minus directly, all these charges have to take like the scenic route all the way around as it comes out. Here, let's use a different color. As it comes out of the positive end. Ooh, I don't like that. Here we are. As it comes out of the positive end, it'll go around like so, and then go through our resistor. Now, of course, even though the resistor is here on this right side, the entire flow is affected, right? Just imagine having a car accident on the freeway that's really far away, but you're going to feel the effects of that accident further down, further down, and so everything is slowed down because of it. But interestingly enough, our analogy breaks down in that usually on in a real car accident on the freeway, the flow starts to increase after you pass the accident, right? Because as soon as you stop watching the accident and you pass it, then you can start to speed up and get to your destination. Unfortunately, that analogy kind of does not work in that even though you pass the resistor, the flow is still slowed down. The flow is dependent on the route itself, not where the resistor is. Okay? If you're going to take this pathway, because that resistor is here, it's going to affect the entire pathway, not just where the resistor is. Okay? The reason being, there's a far more complex answer. It is because a charge doesn't necessarily just move out of the battery and then kind of carry along its way all the way to the negative charge. Technically, it'll do that over a large period of time. Okay. In reality, what happens is that one charge pushes its neighbor that's already here. The wires already have the electrons in them. It's just the battery kind of applies a force onto them that pushes them forward. So when one charge comes out of the battery, it pushes the one that is already here over, and the next one pushes the next door neighbor over, and kind of like a domino effect, each little tiny charge that is inside the wire pushes the next one over until that push translates all the way to the bottom side of the battery. So that one electron or charge, positive charge that is here will essentially move into the minus sign when one of the positive ones comes out. So a high potential positive charge comes out, and then a lower potential one goes into the bottom. That's because it lost energy as it went through the resistor. Okay. Therefore, the direction of the current is always going to be from the positive side of the battery to the negative side of the battery. So if I'm up top here, the current is to the right. High. Okay, so that's the top side. We have a bunch of symbols, and we have our Ohm's law, and that's our primary equation that we'll use, V equals IR. And our simple circuit. Alright, hello, I am here. Hey, there's Alan. Alright, so here's bottom, bot side. Bot side. Current is the amount of charge flowing through a medium. So yeah, we're almost done. Current is the amount. Oh, I don't like that spacing. Let's change it up. There we go. Is the amount of charge flowing through a medium. Flowing through a medium. And I, remember the definition, current is equal to the amount of charge, delta Q, over the amount of time it takes, delta T. Next up, the SI unit. The SI unit for current. Is amperes. Is the ampere. Here, A, aka also known as amps. Oops, not and so we should know that 1 amp is equal to 1 coulomb per second. Okay, so it's a rate. It's how many coulombs of charge you get per second. Alright, current flows easily through a conductor. So let's see. Current flows easily through a conductor. Remember, conductors allow the electrons to flow through them. Chemistry students, you should know that metals make metal bonds where you have this sea of valence electrons, and so through this sea, the electron clouds mesh together, allowing a channel, an ocean for the charges to flow through easily through a conductor. But not. Uh-oh, is my battery letting low? Yeah, kinda. Conductor, but not through an insulator. Okay. Let's see. Oops. Let's just undo. There we go. A conductor. Remember, low resistance to current flow. So a metal is not a very good resistor. Remember, it is a good conductor, so it allows it to move freely. Wires are made of copper. It's nice and cheap. It's readily available, and it's a pretty good conductor. So even though wires may be colored on the outside, that's just insulation to protect itself. But on the inside, if you actually cut a wire open, you'll see that there's copper metal inside. So insulator has high resistance. High resistance to current flow. Resistance is a measurement of resistance is a measurement of okay, well, R, which is rho resistivity of the material times the length divided by the cross-sectional area A. Okay, so L, of course, is the length, which is in meters, the length of the wire or resistor. Or the wire acting as a resistor. But of course, in a diagram, wires have zero resistance. But it is possible to use various combinations of wires or metal to serve as a resistor. Cross-sectional area A. All right. Chat, how do we measure area in SI units? Ooh. Type in chat if you know what the units are for area. Let's see if anyone will get this. Hint. When I measure length, we did it in meters. So if I wanted to do area, I would measure it in... Anyone? Going once? Going twice? There it is. Speedy Cat gets it. Speedy Cat, you are wonderful. You're always fast. Haha. Meters squared. Alright. And rho, this curly P thing, remember it's rho, R-H-O. Rho is the resistivity of the material. Resistivity and resistivity constant. Each metal, or every combination of metal, have a wow, the lag. Yeah, I remember it was like a 9-second lag or something for if you're watching it on like your phone. For some reason, the phones have way more lag than on the computer. Resistivity constant, and it is measured in ohm meters. Ohms, omega, times meters. Ohm meter. Okay. Ohm meter. Okay. So as you can see, it's resistivity times length. So you have ohm meters times meters, which is ohm meter squared. But then you divide by meter squared. That gets rid of the meter squared, leaving you with ohms. Yay. All right. Chemistry students, you should know that resistivity is inversely proportional to conductivity. You got that, Liam? So 1 over conductivity equals resistivity. Hey, we have another follower, Baron Trump 2036. Oh dear God. Well, it's not Trump, it's Trump's little son. The SI unit for resistance, let's see, the SI unit for resistance Yeah, he just wants to learn physics. Let's make the world a better place by teaching everyone physics, even Trump. The SI unit for resistance. Oh, is that another follower? Jeez. Oh, Alan K followed. Oh, let's see. Let's put it in follower. Is that how it... Ah, I see. Z-Physics enabled followers only mode for this room. So this means that you can only chat if you are following. That's how you get followers. Resistance is the ohm. No, it's fine. The more followers, the better, right? And I believe if you're a follower and if you have like the app, it'll tell you whenever I go online, and so you can tune into the stream, etc. So 1 ohm, we're almost done. We're at the finish line here. 1 omega, or 1 ohm, is equal to 1 volt per amp. Volt per amp. Okay, how do you get that? Well, if you use Ohm's law and you divide both sides by amps, you'll see that it's V divided by I equals R. Voltage over current equals resistance, so we have volts over amps. I always knew he'd make it big on Twitch. Yeah, I'm even streaming video games. So, we'll see. It's my retirement plan. Yeah. All right, so that is all for the notes part. Let's go and review real quick. I did. I got carried by my former students. Actually, like, some of my former students have reached out. They want to like get a game in or something. So, yeah, he went mega gaming. Yeah, so if you, even after you graduate, feel free to, stay on stream. This will be a way for us to connect even after you graduate and leave Elko, so you can get a game of League or whatever the new thing is at that time. I'm sure every year it changes to something new. All right, for those of you who just tuned in, remember the title is Current and Resistance. This is Flippy number 6. Flippy number 6. 40 years, yeah, right. I'm not teaching for 40. I don't want to be like one of those super old teachers, typically when you're like super old, the kids are less likely to listen to you. So I don't want to be one of those guys. I want to retire, in my prime, kind of like Michael Jordan, Go out as soon as I hit my peak, and then I'll train someone new, and they'll take the mantle and carry the torch. That's the plan. I want to retire before I'm super old so I can, start my streaming career. Nah, no thanks. My new job is Twitch streamer. Liam went back to bed. Oh my, yeah, that's because he was FaceTiming at 4 a.m. apparently. Ay. Alright, so top side we have our circuit symbols. The battery is big line, small line. And remember, the big line is the positive end and the small line is the minus end. Big line, small line. Okay. Oh, thank you, Dennis. Thank you. Resistor is the squiggly. Resistor is the squiggly. Or sorry, zigzag, I should say. Zigzag. A wire is just a straight line. Anywhere you see a straight line, it's a wire. So if you look at this circuit symbol, like all of this stuff here at the top is all wire. Everything up to the resistor is all wire. Okay, everything below the resistor is all wire. And here we have our battery and our squiggly zigzag thing. That's our resistor. Light bulb. Alan is Baron. No, Alan is Alan K. I don't know who Baron is. Baron, who are you? Yeah, LNK3 is oh, it's Garrett. Hey, Garrett. Uh, uh, Gary, you woke up early. Is this the first time you're waking up early? Well, welcome. We're glad you're here. Yeah, Garrett from Period 6. More Period 6. Giorgio's not the only one. He's uh G Ret. Yeah, we mean G Ret. Where's Aryan when you need him? It's usually Aryan who says that every time he comes into class. Alright, anyway, the light bulb is the squiggly with a circle. We have our switch, which is like a drawbridge. When the bridge is up, that means the cars can't move. And so then the switch is off. You know, the circuit is off. Nothing is working. You have to push the circuit or the switch down. So that's when you turn it on. You push the bridge down so that the charges can move from one side to the other. Okay, we have our new equation, V equals IR, that's Ohm's law. Okay, and finally the circuit diagram. So we've connected some wire to a resistor, and then the resistor is connected to a battery. As soon as you have this pathway, you're set, your circuit will be running. The charges will come out of the positive end, go through the resistor, and get to the minus end. Get Josh, Iggy, and Bella. Alright, I suppose that is all. Is there... Here, let's see if I can find a meme. Oh, wait, no. I guess we'll do one extra slide here. We'll do one extra slide. Voila. We'll talk about this picture the next time, which is tomorrow. Yeah, sure. Let me find the meme. But while I find this meme, I go and write this down, jot this down. This is we've added a switch to our circuit. We have a squiggly with a circle, which is a light bulb, and then some batteries. So this simple circuit is what's inside a flashlight. So if you have a flashlight, this is what you have inside. Why not both? A physics meme or just a funny meme? Yeah, I know, right? So, here we go. All right, I found it. It was on our calendar, which I haven't put up yet. I need to fix our website too. I have lots of work to do. All right. So anyway, this slide is showing you how a flashlight works. Okay. And in order to have a working circuit, you need two things. Here's a test-like question. What are the two things you need in a circuit? The two things you need is an energy source, so something to provide the power. It could be batteries, or you could connect it to the outlet. So the wall outlet also gives you power, right? Technically, that's called AC current or AC alternating current or alternating voltage because the current is alternating. But the battery is a DC, which gives you a constant supply of the same voltage. All right, so you have some battery, the power source, and finally the second requirement is a closed loop. So as long as your pathway is closed, there's a route to go from the positive side of the battery to the negative side of the battery, then your circuit will work. Now, if you don't include anything else, okay, if you have zero resistance in the circuit, then you have infinite current or something like that, which will short circuit the battery and destroy the battery. Okay, so typically you want to also include a load. The word load represents anything that can take away the energy. So load is a universal term, an umbrella term for anything that uses up the energy. So a resistor uses up energy, therefore a resistor is a load. A light bulb uses up energy, therefore a light bulb is a load. And on and on. There are other things that you can have in the circuit that can use up the electrical energy, electrical potential energy, and convert it into something else. Chat, what does a resistor convert electrical potential energy into? What happens? What does it become when it uses up the electrical potential energy? Anyone? Speedy Cat, do you know what happens to the electrical potential energy when it goes through a resistor? Ooh, this one got everyone. Alright. Well, here's a hint. It resists. Very good, Maddie. Here's a hint. If you have an electrical heater, what does the heater do? Well, the heater gives you heat. Yeah. Resistor uses up the electrical potential energy and turns it into thermal energy. Thermal energy is the answer. It turns it into heat. Alright. Alright, so here's our meme. I found it. Here it is. Boom. It says join the resistance. And all these monks are saying Om. And with that, we are finished for the day. Thank you for tuning in. I will see you next time. Bye-bye.